Hey everyone, for our friction experiment, we are investigating the relationship between the coefficient of friction and the position of the contact area between an object and another surface. We know that changing the contact area of an object to a surface does not affect the coefficient of friction. But what if the contact area of the surface remains the same, but the placement of the contact area is changed? In other words, the contact area is not bounded by one area, but it is chopped into different areas and scattered along the face of an object. Will the coefficient of friction change? This diagram illustrates this. The green squares represents the contact area. We see that we can investigate the proposed scenario by spreading the contact area from the middle of the object's face outwards to its corners. Noted that they all have the same contact area, and we can achieve this in an experiment enforcing dimensional restrictions in Photoshop. To do this, we need a wooden board, cardboard cutouts, tape, table stand, and a phone with an inclinometer app. The same wooden board is used throughout the experiment to maintain the same value of normal force. To create the different scenarios, we just have to tape the cardboard pieces in an allocated place. Before experimenting, we ensured that the surface of the table stand is flat. We did this by measuring the angle using an inclinometer app, and it shows the surface is 180 degrees. To do the experiment, we placed the wooden board and the phone with the inclinometer app onto the table stand. Then we slowly increase the angle till the point the board begins to slip. Then we would just record the angle at which it slipped. For scenario 1, the board slips at 19 degrees. For scenario 2, the board slips at 21 degrees. For scenario 3, the board slips at 22 degrees. For scenario 4, the board slips at 21 degrees. For scenario 5, the board slips at 19 degrees.
To find out what happened, we can use the concept of friction. Friction is a force that opposes the motion of an object when two surfaces come in contact with each other. This was seen with the cardboard cutouts and the wooden board. From the experimental results, the angle of sliding is pretty much the same, despite the different placement of contact areas. No significant trend can be observed. The slight variation can be due to several factors, such as inconsistent elevation speed of the ramp, misalignment of the phone, not exact surface area used due to the uneven surfaces of the cardboard pieces, or slight offset on the object's sliding position. So the angle of sliding can be assumed to be constant. Through the formula U equals tan theta, we can say that the coefficient of friction is constant. In scenario 2 and 3, the angle of sliding is around 21 degrees. This means the coefficient of friction will be tan 21, giving us 0.38. This is closely the same as the experimental result of scenario 4 and 5, which started falling at around 20 degrees, which is tan 20 is 0.36. We can see that the coefficient of friction does not change as distribution of contact area changes. This is because where the friction happens, it does not affect the magnitude of the friction force, but only its position. Principally, friction force only depends on weight and roughness of the contact surfaces. Same wooden board is used, so the normal force acting on the board is constant. Through the formula friction equals U normal force, friction force is equal to the normal force times the coefficient of friction. The coefficient of friction and the normal force is constant. Therefore, the friction force acting on the board in all 5 scenarios is the same. What we can do further is to repeat each trial 3 times and use the average for a more reliable result. Also, we can investigate the coefficient of friction using different materials.
For our first experiment, we are doing a force analysis on the candle holder. We want to predict the change in magnitude of a support force reaction when different weights are placed on the candle holder at different locations. By using equilibrium principles, we can predict the change in magnitudes through calculations and then verify them using a digital scale. For this experiment, we used a candle holder, scale, a book, and some chocolate eggs as weights. To set up this experiment, we placed the candle holder on the book and the scale, left support on the book and right support on the scale. The scale will allow us to see the reaction force from the right support. To perform moment calculations, we need to find the distance between reaction forces and the applied loads. We measure this by using a metal ruler to measure the distance between the leg supports and the holder slots. This is where the weight force will be applied to the system. We see that the distance between the candle legs is 8.2 centimeters. The distance between the shortest arc is 6.8 centimeters. The distance between the middle arc is 11.5 centimeters. The distance between the longest arc is 14.8 centimeters. Before doing the experiment, to ensure the surface that the candle holder is standing on is flat, we measured the angle. For the weights we are using, they are little chocolate eggs. The scale we are using are not sensitive enough to get the exact weight, so we have to weigh 5 eggs and average the total weight to get an estimated weight for each egg. We are assuming the minor differences in the weight are negligible. The weight is about 8.3 grams. To investigate the change in reaction force from the right support, we set up 4 scenarios. For our first scenario, we placed the weight at point 1. For our second scenario, we placed the weight at point 2. For our third scenario, we placed the weight at point 7. And finally, for our last scenario, we placed the weight at point 2 and 5.
The candle holder and the chocolate egg experiment demonstrates an important equilibrium principle. The sum of all forces and moments must equal zero in a stationary object. There is the weight force of the candle and the egg acting on the body of the system, which causes the pivots A and B to have reaction forces. This was seen by placing the egg on the candle holder in different places and observing the change in the scale set under pivot B. For the purpose of determining the equilibrium of the system, the center of the mass of the candle holder can be assumed to be concentrated at the exact middle of the candle holder. The center of gravity will be closer to the side where most of the weight is located, therefore one pivot will experience more reaction force than the other. In scenario 1, the egg was placed towards the left end of pivot A. There will be a weight shift causing the center of mass of the system to move closer to pivot A, and therefore experiencing a larger reaction force compared to pivot B. Through moment calculations, we were able to determine that the scale should experience 1.14 newtons upwards, showing 115.8 grams, which followed closely to the experimental result of 116 grams. The second scenario showed the egg being placed closer to the center of the candle holder, which causes the system's center of mass to shift again. The experimental value of the scale at pivot B was 170 grams, which again followed closely to the theoretical value of 180 grams, with pivot B experiencing 1.16 newtons upwards. The third scenario was when the egg was placed vertically on top of the system's center of mass. This would mean both pivots will experience the same reaction force as the egg is acting downwards uniformly to the body of the system. The experimental results show that at pivot B, the scale value was 123 grams, which is similar to the theoretical value of 123.8 grams, with pivot B experiencing upwards with 1.21 newtons. The final scenario was when two identical eggs were placed at two different positions shown. The center of mass was shifted once again, which caused the experimental value of the scale at pivot B to show 134 grams, compared to the theoretical value of 130.3 grams, with pivot B experiencing 1.28 newtons upwards. The slight variation in the experiment and the theoretical value of the scale could be due to several factors, such as the scale not being calibrated or positioned correctly, the eggs not being identical in weight, the fact that the candle holder is not truly uniform in mass, assumptions of the egg's weight as point loads, or human errors in distant measuring. Thanks for watching our experiment.